So yeah, so today, or let me share my screen. So, uh, oh, there it goes. So yeah, so today, I'm going to sort of begin the discussion of actually doing the analysis for generalized Ricci flow. Um, I guess, I don't know, I have it full screen on my screen, so I guess I can't see the chat window. So in any case, please just, I guess, talk if you have a question. And if someone sees something in the chat window, please just let me know. Um, yeah, and so the discussion is going to be, I guess, for those who have seen this kind of analysis for Ricci flow, it's maybe nothing so new really, or in any case, the no real new techniques are needed to get the basic story of existence and regularity going. But we'll eventually see some unique features. I mean, we'll see some, I guess, unique features even today, but eventually as we go farther, we'll see some features unique to generalized Ricci flow. And I'll try to highlight also just some basic questions related to existence regularity that are still open. So let's just recall basically what's going on with generalized Ricci flow. So again, the equation from the classical point of view. So I fix a smooth manifold, Mn, and a closed three form, call it H naught. And then we have a one parameter family of metrics, GT, and then two forms, BT. And we say it's a solution of generalized Ricci flow if this system of PDEs holds. So G is evolving by minus twice the Ricci tensor plus 1/2 H squared, where this H squared tensor is as before. And then dBdt is minus d star H, and H is this background three form plus dB. So B is like some kind of potential for the moving three form H. And then, so Mario sort of discussed last time how this sort of looks. Whoa, excuse me. How this looks like from the point of view of generalized geometry. So to just sort of say the same thing in a different way. So if we have E over M, an exact Courant algebroid, so this is just T plus T star. So E as a vector bundle is just T plus T star. And but it has a Courant bracket, which is maybe twisted by this background three form H naught. Then we say a one parameter family of generalized metrics GT. So these are endomorphisms of T plus T star, which satisfy these axioms. So we say these are a solution of generalized Ricci flow if we have this equation. So G inverse ddt G is minus twice this sort of Ricci endomorphism, again, that Mario discussed. And the particulars of this are not really super relevant today, but just to sort of briefly recall the way the equivalence works. So again, this background three form present in the classical picture sort of corresponds to the twisting of this bracket on T plus T star, twisting of this Courant bracket on T plus T star. And the way you sort of explicitly recover the equivalence is that, so this GT is an endomorphism which squares to the identity. And so it has eigenvalues of plus minus one. And the eigenbundles corresponding to those eigenspaces are called V plus minus. Those are some subbundles of T plus T star, and they're sort of canonically identified with the graphs of B plus or minus G, interpreted as maps from T to T star. So the graphs of those are some subbundles in T plus T star, which are V plus minus. So in any case, just sort of chasing through these elementary definitions allows you to recover that this generalized version of the equation is just the same as this more classical version. Okay. So the first thing we want to know in studying the analysis is the short time existence of the flow. So and the ideas related to this are, of course, thematically very similar to what happens in generalized Ricci flow. So, so the first thing you might want to do is just sort of examine what this PDE looks like in coordinates. And in particular, if you make a special choice of coordinates, these so-called harmonic coordinates based at some point, and then you look at what this equation looks like, well, it can be expressed as follows. So the time derivative of the, of Gij, so I'm working in local coordinates here, is G upper KL del squared Gij by del xk del xl plus some lower order terms, some nonlinear lower order terms. So in particular, this appears to be a parabolic equation. So the symbol of this operator on the right hand side, at least in these special coordinates, appears to be just like that of the Laplacian associated to G. So in this naive way, Ricci flow appears to be a parabolic equation, but you kind of can't really begin the story that way because this really only holds sort of at one point at one time in some special coordinates. So you can't really work this way. And
can I ask a question?
Yeah, please.
Yeah, this is really basic, but can you say what is a parabolic equation?
Yeah, so well, so maybe just a moment. Let me maybe let me log in with my phone. In just a second. Sorry. Wow, gosh, there it is. I just need the meeting ID. There it is. So I mean, in a nutshell, like the prototypical parabolic equation is like the heat equation on Rn. This is sort of the prototype. Let me just join with my phone, anyways, though, just for later. Nice. And so, how do I? Just a moment. Sorry, just a second. Where is it? Yeah, so right. The sort of I guess can you see my paper here?
Yeah, I can see it.
No.
Okay. Or do I have to like stop the screen share to? In any case, yeah. So if we take this basic operator, say Lu is ddt minus Laplacian u, where Laplacian, this is just on Rn, is sum del squared del xi squared I equals 1 to n. This is the most here. Let me just stop that. So I can see it on my screen too. This is like the most sort of basic example of parabolic equation. But more generally, you might, I mean, what's really sort of relevant is, so Lu is maybe ddt minus L naught u, where this L naught u, L naught is some kind of elliptic, second order elliptic operator. So sum Ij equals 1 to n a Ij d squared dxi dxj, something like this, where we impose that this matrix is positive definite, say. And yeah, so the general idea with parabolic equations is maybe you're looking for solutions to like an elliptic equation. In this case, maybe just Laplace equation, Laplace u equals 0, and you find it as the long time limit of a parabolic equation. So the parabolic equation starts with some arbitrary data and then flows it forward in time and sort of smooths it out, and in a perfect world converges to a solution maybe of the corresponding elliptic PDE. And of course, this is, yeah, I mean, this is always the basic philosophy. And for Ricci flow, it's even sort of more like for classical problems in elliptic theory, usually there's sort of an equivalent continuity method approach, which basically recovers all the same results as a parabolic approach. But for Ricci flow, it's not really the case. There's no like sort of elliptic analog really of Ricci flow. So somehow this parabolic method is kind of necessary. But yeah, so then maybe just to go back to the to go back here, so we can sort of recognize this equation in coordinates as having a nice elliptic operator on the right hand side. So the g, of course, in coordinates is positive definite. So this is some nice elliptic operator on the right hand side. So okay, yeah. So more generally, or more precisely, we have to think about minus twice Ricci as some nonlinear differential operator in G, and we can linearize it. So we can just compute the linearization of minus twice Ricci anyways, in the direction of some symmetric 2 tensor H. And this is what you get. You get Laplacian H minus divergence star divergence H. So div is the usual divergence operator, and then div star is its L2 adjoint, and then plus the Hessian of the trace with respect to G of H, plus some curvature term acting on H, like a 0th order term in H. We can compute, so this Laplacian H, of course, is sort of the one we're looking for, but then these other terms sort of cause a problem. And it turns out that sort of as a differential operator, this thing on the right-hand side is weakly elliptic. So it sort of appears as a positive semi-definite matrix paired against the matrix of second derivatives of H, but it does indeed have a kernel. So basically this, it's as if this matrix A that I wrote by hand was only positive semi-definite, but indeed did have a kernel. And so it's, again, you sort of can't apply standard tools to an equation that has a kernel like that, or at least the most standard tools. But as is the case in all these geometry problems, there's sort of a good reason for this kernel. And you can sort of show that that kernel is spanned by variations arising from the sort of infinitesimal action of the group of diffeomorphisms. So again, this is part of a common theme of problems in this area. So basically, we could take any solution to Ricci flow and we could pull it back by a diffeomorphism, and we get another solution. So this causes a problem with the parabolicity, and this computation, or this fact that the kernel is spanned by variations in this way is sort of completes the circle of ideas. So in a sense, the diffeomorphism invariance is the reason why this operator is only weakly elliptic or weakly parabolic and not strongly parabolic. But then luckily, because we sort of know the source.
So is that the only reason why there's a kernel? So
I'm sorry, can you say that again?
Yeah, is that the only reason why there's a kernel? Like, so if you gauge fix in some way the action of this group, then the operator becomes definitely positive.
Exactly. Yeah.
I mean elliptic.
That's exactly right.
Okay.
Yeah, and that's Yeah, that's exactly right. And that's like how the proof of short time existence goes. So I'm gonna discuss that.
Okay.
So yeah, that's the whole point then, is to yeah, like gauge fix the action. And then yeah, right. So okay, there it is on the slide. Yeah. So we overcome this through gauge fixing, which is known as this de Turk method, de Turk trick. Yeah, so we'll sort of implicitly discuss that proof, the proof of short-time existence of Ricci flow, because of course it's inside the proof of short-time existence of generalized Ricci flow. But just to sort of make it a bit more precise, we have this same kind of circle of ideas for generalized Ricci flow. So here's this equation. And again, we can look in harmonic coordinates. And well, this is how it will look. So again, this is sort of a naive point of view. We're picking some special coordinates. But anyways, from the point of view of for the flow of the metric, the Ricci term is giving the leading order term. And again, since it's a second order differential operator, this h squared term is somehow irrelevant from the point of view of just the basic parabolic theory. And then this d star h, the leading order term of that, as far as b is concerned, is d star db. And then there's again some lower order terms. At least as far as b is concerned, there's lower order terms. Although I guess there are no, yeah, it's just first order terms in g and b. So this again is parabolic, but again, there's issues related to gauge invariance. But this time, sort of as Mario sort of discussed and has been implicit, the invariance group is bigger. This is what always happens in generalized geometry. So we have this action of the group of Courant automorphisms. And here you can kind of see, well, I mean, we have the diffeomorphism action that will arise in making the equation for G parabolic. But then obviously, just from a kind of more standard like elliptic theory point of view, this operator for B on the right-hand side is clearly not elliptic, right? It's sort of missing. If that was going to be the Hodge-Laplacian, it's missing dd star B. And that, of course, is sort of connected to the fact that we have this B field action as part of the group of Courant automorphisms. So basically using these two pieces of the symmetry, or we have to gauge fix both of these actions, I guess is the point. But then the fact that what it's missing is something exact, and in particular closed, like this dd star B, allows us to use the Courant automorphism group to sort of fix the equation. Okay, so here then is the statement that we'll prove. So if I have an exact Courant algebroid over a compact manifold M, and I fix G naught, some generalized metric on E, then there is some epsilon positive and a unique solution G sub t to this generalized Ricci flow with initial condition G naught on this time interval. So in other words, this is just the short time existence result. So for any generalized metric on any compact manifold, you can always solve the flow at least for a couple seconds, at least for epsilon seconds. Okay. Yeah, so I discussed how we need to sort of gauge fix this sort of with respect to this Courant symmetry group, but actually, well, in a sense, we are doing it, but I'm gonna do it sort of implicitly. So it turns out to be technically a little bit simpler to work with sort of G and H directly. This I don't think is really completely essential, and maybe I'll say some more words about that. But just from a technical standpoint, it turns out to be easier to work with G and H. This is kind of a standard thing. Like in a sense, H is kind of like a field strength associated to B, and B. We sort of solve everything in terms of H, and then recover B after the fact. Okay, but somehow working all this out directly for pairs G and B, I think could be interesting in some settings, and perhaps even preferred. But yeah, so what I'm going to do is, I forget, I think Mario said this, but it's probably worth saying again, that the induced evolution on H, so H by definition is H naught plus dB, and so you end up getting minus dd star sub g h. Of course, ddt h naught is 0, but h is closed, so this is just Laplace dh. My Laplacian includes a sign in it. So along a generalized Ricci flow, this is the induced evolution for h. And so we're going to sort of temporarily forget about B and just solve this system instead. Okay, and then once we have that, if we can just solve this equation, then you can literally just treat this equation for B as like an ODE in each fiber and just integrate, and it will solve the equation it's supposed to solve. In other words, the given H will be H naught plus dB sort of by construction. Okay. So yeah, so the first step is to establish short time existence, not of this system I wrote before, but of a gauge fixed version. So in particular, given a metric, standard metric little g, and some fixed background metric g naught, this can be the initial data, but it doesn't even really have to be. It can just be some background metric. We can define a vector field by using these two metrics. And how is it defined? We take the difference of the Levi-Civita connections, and then we so this is a one form with values and endomorphisms of the tangent bundle, and then we trace the two down indices with the metric G. Okay. Now, yeah, so maybe some of you have not seen, but this is exactly the sort of vector field. In any case, the proof I'm discussing is sort of piggybacking directly upon the standard proof of short time existence for regular Ricci flow, and this is exactly the same vector field which is used there. But it is interesting to point out that actually, I mean, it's just sort of used as some device, as well, some sort of analytic device, but it actually does have a natural interpretation in terms of generalized geometry. It's the difference of divergence operators associated to the moving generalized metric and a background generalized metric, as discussed by Mario. But in any case, once we have this vector field X, we can define some new differential operators. So I call it O1 of a metric and a 3 form, which is our sort of generalized Ricci flow term, minus twice Ricci plus 1/2 h squared, plus this Lie derivative term. So the Lie derivative with respect to this vector field X of the metric G. And then similarly, I define O2. O2 is the Hodge-Laplacian of H, plus again this Lie derivative term. So the Lie derivative of H with respect to this vector field X. Okay, so the key computation that I'm gonna skip, I mean, this is just some grind, but it is, of course, an essential point in the story, is so we can compute the symbol of the linearization of this differential operator. This is as a so my like linearized variables are h and k. So unfortunately, there's kind of two meanings of h. So like g dot is little h and big H dot is capital K. So anyways, it's not maybe the best notation, but there it is. So the symbol of this differential operator is lower triangular, and along the diagonal we just have the Laplacian. Okay. So the point is, what that means is that this associated, so to just connect back to what I was saying before, this coupled differential operator O1, O2 is strictly elliptic. Okay, so like this matrix is clearly invertible, right? And sorry, positive definite, even strictly positive definite. So so that means that this equation, where I include these Lie derivative terms on the right hand side, this sort of gauge modified generalized Ricci flow, is indeed a strictly parabolic system. So yeah, just to sort of summarize, if you as we sort of mentioned before, like just only consider like the metric part, like this O1, like the symbol of the linearization of Ricci is not strictly positive definite. But by making this specific choice of gauge action like this, so by making this, by adding this specific Lie derivative term, it becomes a strictly positive definite. And then the equation for H is sort of not affected by this, actually. So in a sense, we've already rendered the equation for B parabolic, because we're not really thinking about B, we're just working at the level of H, and that equation is already parabolic. And then this Lie derivative term sort of doesn't affect it doesn't affect the ellipticity of this operator.
Can I ask a question?
Yeah, please.
So the kind of the, I don't know, the cartoon I have about gauge fixing is that you have a group that's acting, which is in the kernel of the operator, and so you should pick a transverse slice and only work on that transverse slice. So is that what you're doing here? It looks like you've added something to the equation to make the kernel 0.
Basically, yes, exactly. Yeah. I mean, I think your description is essentially correct. Yeah.
So how
Yeah,
is that related to choosing a slice?
Right. So right. So like in the elliptic setting, you would think of it as like only considering variations which satisfy some extra PDE, like which are divergence free or something like that. And this is how you think of, yeah, like picking a particular slice. I mean, I guess right, you can't exactly think of it that way anymore. Well, I mean, I guess the inclusion of this term you can think of as kind of breaking the gauge invariant. So the equation is no longer really diffeomorphism invariant in a sense, because of this vector field that depends on this background object G naught. So in that sense, by introducing this term, you're sort of breaking the invariance, and yeah, in any case, the right hand side does become strictly parabolic. But I agree, it's a little bit different from because yeah, usually I guess in the elliptic setting you sort of understand that you only have to consider variations which are already like transverse to the action in an appropriate sense. It's not really quite like that. It's just that the inclusion of this term is sort of changing the operator itself this time. I don't know. Does that help? I'm not sure.
Yeah, I think so. Yeah, thanks.
Okay, yeah. So yeah, so so this system, this gauge fixed generalized Ricci flow, is strictly parabolic. And then so again, we can apply this kind of general theory of strictly parabolic equations on compact manifolds to claim there exists some short time solution. So again, this itself is kind of you know, a lot of work from PDE theory, but it's typically quoted in this context. So we'll just quote it. Okay, but so we did solve sort of the wrong equation, but it's a relatively straightforward matter to sort of, again, now like apply a diffeomorphism action to solve the generalized Ricci flow. So in particular, this is a very straightforward thing. So we have a solution to this gauge modified equation from the previous slide. And then I define this one parameter family of diffeomorphisms, which is generated by this vector field, well, minus this vector field. So minus x of GTG naught. So that defines this family phi t, and then all I have to do is just pull back the solution. Sorry, this should be bar ht is phi t star h sub t, of course. So I define this data g bar h bar by just pulling back by the time-dependent diffeomorphisms, and then it's just a very straightforward calculation to show that when I take the evolution of this pullback data, using the diffeomorphism invariance of Ricci and h squared, these terms sort of transform naturally, and then this Lie derivative term is sort of canceled out by the extra term I get by differentiating phi t star. Okay, so when I take the time derivative of gt bar, I basically get two terms. One is the pullback of dg dt, and the other is the derivative of phi t star, which is of course this Lie derivative term. And just by like some naturality of Lie derivatives, this Lie derivative term cancels this Lie derivative term. Okay, and then again, it's exactly the same idea for h bar. So when I take the time derivative of h bar, I have to take the time derivative of h and then pull that back, and then I also get the Lie derivative term arising from the time derivative of phi t star. And when you carry that out, it just exactly has the effect of killing off this Lie derivative term. Okay. So yeah, we took our solution to the gauge modified flow, and then we pulled it back by the relevant diffeomorphisms and just sort of killed off this extra term. So that at least shows the existence, but there's still a subtle point remaining. So maybe I just quickly go back. So for this gauge modified PDE, the general theory gives you not only existence, but also uniqueness. And then we said, okay, well, fine, we just gauge fix and go back. And now we have at least solved our equation, but we can't immediately conclude the uniqueness, right? Because to sort of construct this solution, we had to like use the solution GT itself in constructing this family of diffeomorphisms. So somehow you can't immediately conclude uniqueness of the solution. And instead, the trick you have to do is to sort of reverse this procedure, and you have to start with a solution of Ricci flow and sort of reconstruct the solution of gauge modified Ricci flow. So let me just say how this goes, because it's a very beautiful fact. So if we have G bar T, B bar T, a solution to generalized Ricci flow, well, again, the goal is that we're trying to sort of gauge modify to go back to the special gauge fixed flow. And so we need to, in a sense, reconstruct what that one parameter family of diffeomorphisms is. So it turns out that what the right thing to do is we let phi t be the one parameter family of diffeomorphisms, which is this solution to this harmonic map flow. So d phi dt is the Laplacian on maps with respect to G bar T and G naught bar. And then phi naught is the identity. So this is, again, I don't really want to get into the details of this. If you've ever seen this harmonic map Laplacian, that's great. If not, it's a natural differential operator, second order differential operator on maps between manifolds, between Riemannian manifolds, that depends on the source metric, which in this case is G bar T, and the target metric, which is G naught bar in this context. And it's a strictly elliptic operator. So this is a strictly parabolic equation. So in other words, I have my solution to generalized Ricci flow, and then sort of along that flow, I'm going to construct this solution to harmonic map flow. And then the sort of totally amazing fact, which underlies why this works, is the following computation. So this is kind of a, in a sense, totally elementary, but also subtle calculation. So if I ask, well, what is this harmonic map Laplacian with respect to g bar t, g naught bar acting on phi t? Well, the right way to think about it is you sort of pull the computation back, and it's the Laplacian with respect to the pullback of gt bar by phi t inverse of the identity map. And then you just sort of compute out what this is in coordinates, and then magically it is this vector field minus x with respect to the pullback metric of gt bar. So this is a very delicate point. So the point is like this operator, this operator x, right, was the difference of connections. This is like a first order operator on G, and moreover, this will end up being sort of like first order in phi as well. Whereas this operator on the left is obviously like a second order operator in phi. So the point is, by sort of expressing this same operator once with respect to g bar t and then once with respect to the pullback of g bar t, it kind of has these different faces to it. So in particular, it's recovering this vector field x from before. So what that means, so in any case, this is definitely some subtle calculation that has to be performed, but the consequence of it is really simple. What that means, once you know this, is that if I then pull back g bar t by the inverse of these diffeomorphisms phi and similarly h, then this pair GT-HT solves the gauge fixed flow. Okay. So basically what we did, the first time is we sort of declared this special gauge fixed flow. We solved that, and then we gauge fixed a way to solve the Ricci flow. Now what we're doing is we're starting with a Ricci flow and then sort of constructing the relevant gauge operator, you could say. We're constructing the relevant one parameter family of diffeomorphisms to sort of take it back to a solution of the gauge fixed flow. Okay. So the point is then that basically this harmonic map flow for phi has unique solutions, and then the gauge fixed Ricci flow has unique solutions. So therefore the Ricci flow itself has to have unique solutions.
I'm sorry, can I have a question, Jeff?
Yeah.
So if I remember correctly, in the Ricci flow, you usually you have to solve this backwards heat equation for scalar function f, right? It's one of the way to reproduce what you're solving, what you're showing.
No, I think this is different. You're thinking of like this function little f, like from this like Perelman f functional.
Yeah.
This is kind of auxiliary. I mean, that's not really directly related to short time existence. I mean, you do end up like using those scalar functions little f to like put the flow in special gauges, but that's not quite what this is.
I see.
Like that's all done kind of after the fact. Like you have a Ricci flow. You can solve this backward heat equation for the little f. I'll talk about this probably not this week, but next time. And then you sort of gauge modify the whole thing to get this sort of flow in like this Perelman gauge, this special gauge.
Okay, so it's a different thing from
But
this.
Yeah, it's a different issue, I would say. Yeah.
All right.
I mean, in particular, like this vector field x, I don't think is really ever like a gradient vector field, or at least not usually. I don't think.
Okay.
Yeah. Okay, so that concludes the proof of uniqueness, of existence and uniqueness. But I just want to sort of point out a few things already, sort of at this very basic level, that are well, still missing or still to be done, even though in principle they should be relatively straightforward extensions of what is known for Ricci flow. So in particular, when I quote this hammer of saying, well, I have a strictly parabolic equation on a compact manifold, I can just solve it, at least for some short time, we can then ask, well, what about short time existence for when you have complete initial data? So if you had a complete Riemannian manifold, complete initial data, and you want to solve this generalized Ricci flow, and you have to definitely impose some kind of hypothesis, like maybe the initial curvature tensor is bounded, something like this, and you can try to prove short time existence. And this was done for Ricci flow by Xi, and probably more or less these same methods that he uses could probably work to prove a similar result for generalized Ricci flow. And I guess by now there are many results recently for sort of trying to weaken this hypothesis more and more. So how weak a condition on your initial data can you allow and still prove that the Ricci flow has a solution? Also, there are some interesting questions. So for Ricci flow, there's now like a backwards uniqueness result. This was proved by Kashvar, and so what this means is if you have two solutions, say on a time interval like 0, 1, and the data agree at time 1, do they have to have agreed for all times before that? That turns out to be true, at least for compact manifolds. This is true, and in particular, this has some nice effect of showing that the isometry group for like finite times never changes. So we have this idea that like Ricci flow, flows maybe some random metric on the 2-sphere to the round metric. So the isometry group does improve, but it does so only like at infinite time or sort of at some singular time. Also sort of related to the same ideas, is the holonomy stable along a solution to generalized Ricci flow. And again, for regular Ricci flow, this was proved by Kashvar. It's related to this backward uniqueness question. But there somehow even, I mean, it's sort of, we've begged a much more basic question, which is what even really is the right notion of holonomy for generalized geometry in general, and let alone generalized Ricci flows. So maybe one means the holonomy of the Bismuth connection, or maybe we need some notion of holonomy for these generalized connections. It's not really clear what notion, if any, is relevant to this generalized Ricci curvature, or let alone generalized Ricci flow. But so still an interesting question. Also, just sort of as a curiosity, so this harmonic map flow ends up sort of rearing its head in this kind of surprising way in showing the uniqueness. But I wonder if one tries to carry out the details of short time existence for the GB flow directly, probably I would wonder if you end up sort of needing to modify the flow by what amounts to the sort of negative gradient flow of this sigma model energy that Mario defined earlier. Because of course the sigma model energy with no H around is just the harmonic map energy, basically. So I wonder if it has something to do with that. But again, I think this is probably mostly a curiosity, although maybe for problems like on complete manifolds, it might offer some subtle analytic advantage to do things with GB directly. I don't know. But okay, so that's the existence, and right. So I probably won't get through everything I had hoped to, but I'll just sort of begin the discussion of regularity. So so we have these short time solutions, and then the question is, well, how long does the solution exist, and what does it do, and how does it stop existing, right? This is the standard sort of circle of questions one asks about problems like these. And so I just want to recall a handful of fundamental results in this direction, which are sort of basically due to Hamilton and Xi. And the first fundamental point about Ricci flow, and this is sort of a general thing coming from parabolic theory, is the sort of smoothing effect. So it looks like this. So if the Riemann curvature is bounded by k on an interval roughly of the form of length sort of order 1 over k, so some little constant over k, then what happens is that on that time interval, all the derivatives of curvature become bounded at some precise algebraic rate. So in particular, the norm of the kth derivative of curvature is roughly bounded by capital K over t to the little k over 2. So each derivative sort of becomes bounded as t pulls away from 0. Also, we can characterize the maximal existence time. So just by some general arguments, once we have some solution to Ricci flow, it will exist by some formal arguments on some maximal time interval. And actually what I state here is not correct. It should say if t is finite, if capital T is less than infinity. So if it stops at some finite time, then the curvature must go to infinity, at least in this way. The lim sup as little t goes to big T of the norm of curvature has to go to infinity. And then another fundamental principle in understanding Ricci flow is the idea of compactness. And so again, I'm going to state this imprecisely, but we'll sort of come back to it. So sequences of solutions to Ricci flow with uniformly bounded curvature on compact subsets of space-time and a uniform lower bound on the injectivity radius. And again, you have to be a little bit more precise about this, but in any case, this is the basic idea. We'll admit subsequences which converge in this Cheeger-Gromov sense to a solution to Ricci flow. So this is a fundamental tool for various applications. So like, for instance, you have some solution that exists for all time and you want to know what's the limiting behavior at infinity. Well, you want to take some kind of limit, and this is the sense in which one takes these limits. And of course, also, like if you have a singularity and you want to do some kind of blow up of that singularity, this is the tool you use to construct. Yeah, please.
How does the second point relate, or like in the first point, I thought it was saying something about the curvature being bounded, but then in the second point it's
well, so in the first one, the curvature bound is a hypothesis. So I'm like assuming I have a bound on the curvature on some time interval. And then the point is, you know, in the presence of this relatively strong information of the curvature being bounded, then all the derivatives of curvature become bounded. So you have to sort of think of what's happening on, say, like after halfway through this time interval. So once t has some lower bound, then this is telling you that every derivative of curvature has become bounded. But you know, the point of this is that, you know, it has this strong hypothesis that the curvature is bounded. And then you can just go a little bit farther and say, well, if somehow the solution stops existing, then this hypothesis has to have been violated. Like this curvature has to have gone to infinity, basically.
And why would the curvature go to infinity, given that from what you said earlier, the expectation would be that it would become 0?
Oh, did I say that?
Well, I don't know if that's what you said, but you said.
Yeah. Well, I mean, this can be seen in really elementary examples. So like, for instance, here maybe. Like the simplest example of Ricci flow. So I can take, say, G on Sn, like the round metric on Sn, and so the Ricci tensor is I guess n-1 times G, depending on your normalization, GSN, right? So this is just the round metric, and you can just do the explicit calculation. So if you start Ricci flow with this initial data, so GT is it's 1 minus I guess twice n-1 t GSN. I think I did it right. So so if you just solve the Ricci flow with this initial data, with the round metric as initial data, it just shrinks in, this exists on a time interval 0, 1 over 2, n minus 1. And so all that's happening, right, is that it's just shrinking homothetically, right, to a point, and then the curvature, the curvature is of size like 1 over 1 minus, sorry, 1 over like 1 minus t over 2 n minus 1 or something like that. So the point is, as t goes to this I did it wrong. 2 n minus 1 t. The point is, as t goes to this magic value, it's of course blowing up, right? So the radius, everything is sort of size 1 over the time to this blow up, basically.
Oh, so I guess the thing that you said before was that the heat, when you solve the heat equation, it will take the.
Yeah. So okay, yeah, like, so for like a linear heat equation, like just for like functions on a Riemannian manifold, the linear heat equation will always exist on an infinite time interval and will always converge to a constant function. But in these nonlinear settings, yeah, you cannot expect that, and sort of like the geometry of what's happening at singularities is the whole game.
And it has something to do with if it's positively curved or negatively curved, or.
Yeah, of course. Yeah. So this yeah, so there's this whole sort of family of results where if you start with some kind of nice curvature hypothesis and then nice curvature positivity, then maybe you see behavior which is asymptotically like a shrinking sphere. There's a whole family of results. And so like the first result on Ricci flow is Hamilton's result, proving that if the initial Ricci curvature is positive, then what you see is a finite time singularity, which is asymptotic to this example, basically. Yeah. So, okay. Let me go back. So yeah, wait, what time is it? So, okay, maybe maybe I just talk for a few more minutes, and then maybe we call it. So, right. So we're gonna discuss some results. So maybe I just quickly go back. I mean, these are the most kind of generic type of results for Ricci flow. It's a very sort of like broad manifestation just of the fact that it's a nonlinear parabolic equation. Basically, there's not a lot of fine structure to this. So the point is, there are results of this kind for generalized Ricci flow, which follow in a very similar way. But again, I will point out some of the unique features. And actually, one of the interesting starting points, which again, it plays a role in a sort of deeper role as you go on, is that if for generalized Ricci flow, it turns out the sort of curvature will bound the torsion. And what I mean by that is, like, so we have these two objects, like G and B, or G and H anyways. And it's sort of, if G is controlled, if the Riemannian curvature is controlled, then H will also be controlled. And so how does this work? Well, to begin with, so we just remember, so to begin with, we need to understand what the evolution for the norm squared of H is, and this can be computed. And so what it is, the time derivative of norm H squared is the Laplacian minus this norm grad H squared, plus a certain curvature action, which is Riemann times H squared. But then this is kind of the key point of this calculation, is that there's a fourth order term, which looks like the magnitude of H squared with a coefficient of -3/2. So this fourth order term is negative. This is sort of the basic point in this. So how do we derive this? Well, it's a relatively straightforward calculation. So we want to compute the time derivative of this norm, and of course I'm using the time dependent metric to compute it. So I get twice ddth, and then minus 3 times the inner product of dgdt with h squared. This is how this works out. So every inner product, every norm is the time-dependent one. And then ddth is just the Hodge Laplacian, and then dgdt contributes this Ricci term, but then the point is dgdt has a positive h squared. So this turns into minus 3/2 magnitude h squared squared. And then you just use the Bachner formula and you get some extra curvature term. And then just using this sort of standard identity, this inner product Laplace HH can be converted into these two terms. It's Laplacian norm h squared minus twice norm grad h squared. Okay. And again, even here already is some kind of minor mystery of, so this curvature term is not quite that which arises in the Bachner formula because it's further modified by this 6 Ricci term. But in any case, I don't know of any result that sort of usefully uses the structure of that Riemann term. Okay, but in any case, we can actually do something with this by using maximum principle. And so again, I know probably for some this maybe is review, but let's just do it anyways. How do we apply the maximum principle for parabolic equations on manifolds? So I'm going to fix a smooth manifold with a smooth one-parameter family of metrics, GT, and then XT is some smooth one-parameter family of vector fields. And then I'm going to fix, it's probably more technical than it needs to be for this, but I'm going to fix a capital F, which is just a function which is continuous in the time parameter, and Lipschitz in this x variable r, and then define this semi-linear heat operator. Okay, so L. So LU is ddtu minus the time-dependent Laplacian of u minus this first order term xtu, and then minus this kind of 0th order term using this function capital F. So we call this our semi-linear heat operator, and a basic fact about operators like this is the maximum principle. So this is what underlies all the analysis for equations of this kind. So if I fix now a compact manifold and a one-parameter family of metrics, and also x and f as above, so that gives me L, this semi-linear heat operator. And then I suppose I have two functions, u and v, and I have this differential inequality that LV is less or equal to LU. And then I know that initially V is below U. So initially the sup of V minus U is non-positive. Then the conclusion is that that inequality remains for all time. Okay. So I stated a somewhat technical version of this, but this is really just a slightly souped up version of the very basic fact that if you have a solution to just a standard heat equation on a Riemannian manifold, then its maximum must not increase. It's just kind of a jazzed up version of that very basic statement. Okay, but then we can use that to prove first this very basic fact that that if we have a solution to generalized Ricci flow, capital G sub t, but then the initial torsion vanishes, then in fact the torsion vanishes for all time, and GT is a solution of Ricci flow. So actually, I guess you can prove this several ways. It's a very elementary point, but one way to do it is using the maximum principle, and it sort of builds up to the next argument. So just to sort of connect back to this maximum principle that I discussed on the previous slide, we just take some fixed time interval on which the solution exists, and because it exists, there's some bound on the curvature, just call it k. And then by plugging that in to this previous formula, just in a crude way, I can get the following differential inequality. So So this is exactly just the equality from before, but I've just replaced the curvature term by some crude upper bound, ck magnitude h squared. And then I just drop this negative term and this negative term, and then I get this differential inequality. And then I just define my semilinear heat operator as follows. So Lu is ddtu minus Laplacian with respect to this time-dependent metric of u minus cku. And then we just notice that the function phi, which is just a 0 everywhere in space and time, is actually just a solution of L phi equals 0. That's trivial. And then you can just compute using this differential inequality from above that L norm h squared is less or equal to 0, which is then equal to L phi. But norm h squared is less than or equal to phi at time 0. So the maximum principle tells you it just has to be 0 everywhere in space and time. So I guess you can also prove this by sort of invoking uniqueness. So h is 0, so there is some solution to Ricci flow, which is sort of tautologically also a solution to generalized Ricci flow with h equals 0. And so by sort of using just the uniqueness of solutions to generalized Ricci flow, you can also prove this proposition. But in any case, this proof is fine too. And then, yeah, so we can just give a slightly more souped up version of this argument, which gives this idea of like a curvature bounds the torsion. And how does this look? So if I have GT, a solution of generalized Ricci flow, on an interval of this form, so 0 to alpha over k, and I assume that the curvature is bounded by capital K on that interval, then there exists some constant C such that for all t in a time interval, I have the following, again, like smoothing type estimate. So the supremum of t norm h squared is bounded above by some constant, and the supremum of t times the norm of the gradient of h is also bounded above by some constant. So again, this factor of t is kind of, well, it's necessary. The statement is sort of couldn't possibly be true without it, because I'm only making an assumption really about the curvature. I'm making no other assumption at time 0. So my estimate kind of has to be meaningless at time 0, and indeed it is, right? It only becomes meaningful like as t goes forward from 0. But yeah, so I'll just discuss the proof for norm h squared. The proof for the gradient is very similar. But so again, we remember that we have this differential inequality, or in this case, equality from the previous lemma. And again, we can use the curvature bound to bound this curvature term by just the constant k, basically. But then we can furthermore, so you just have to sort of notice a little bit of algebraic structure about the magnitude of this tensor h squared and just conclude that it does indeed bound some multiple of just norm h to the 4th. And the multiple is 1 over n. But that's an easy calculation. And so when you sort of put this together and also include this factor of t, we can get a differential inequality for t times norm h squared, and this is what it looks like. So this is just some easy fact by including the t, using the inequality above. And then again, by hypothesis, tk is bounded above by the max of alpha and 1. And then I can just sort of rearrange this by factoring out a norm h squared, and then times c max alpha 1 minus 3 over 2n t norm h squared. And then the point is, well, I won't exactly set it up exactly the way that, I mean, you can set this up in the maximum principle exactly the way I wrote it in the previous slide, but intuitively what's going on is so t norm h squared starts out being 0 at time 0. And if it ever gets bigger than this universal constant, then this right-hand side is actually just 0, or sorry, is non-positive. So basically what this is telling you is that then this constant C1 just acts as a barrier for T norm H squared. And so, yeah, so this, by arguing this way, you can apply the maximum principle to show that T H squared can't ever exceed this value C1 on this interval 0 to alpha over K. So okay, I think probably I should stop there. And yeah, and then next time I'll discuss more the sort of other parts of this regularity package, like the estimates of derivatives and also compactness of solutions. And then probably I'll also have time to move on to discussing these Perelman functionals and the effect they have on the analysis. So yeah, thanks everyone. Are there any other questions? Okay, well, yeah, thanks guys for the questions you did have. And I'll see you next week.